and today we are going to discuss about various CNN architectures, the basic CNN architectures which came to limelight and how people start exploring more and more. So we are not going to very advanced CNN architecture. We'll go till the ResNet, which is the advanced one, but we will see that how to read a CNN network and how to code it out. Okay, mostly I might not able to show coding, but I will show you the code, explain the code, because the explanation part is not time, and writing does not take time, but training takes time. So for example, if I want to show you, just to share what I'm going to do today, so let me share the screen once. So today what we are going to do is, I hope you can see the screen now. Okay, so what we are going to do is mostly look at the VGG16 as a kind of a model, a CNN model, and something called as ResNet model. Okay, and we will look at something called as checkpointing and storing, that is storing the intermediate models and all that. So we will see that. I may not able to write. I could have write it down, but the problem was the training time. Training time is running right now from last 20-30 minutes, so it takes a lot of time for training. So that's why I kept everything running such that it takes its own time to run, such that by the time we cover our theory session, we will see that how to read all this stuff, what I'm just printing it out, and various aspect of the code. Okay, so I'll stop sharing this. I will get back to the theory part first, uh, and then we'll start look at the code one by one. Okay, so I'll stop sharing this part. Let me share second device. Okay, so let's start um, from this. I hope the screen is coming. Yeah. Okay. Okay, so let's start with why we are going to see the CNN architectures basically, and to motivate that part, let's understand something called as ImageNet challenge. Okay, so there's something called as ImageNet challenge, which is which makes actually make the deep learning quite popular into the mainstream thing, because it has the challenges of like this image classification, where given a image like this, I have to predict what is that image called as. I have to divide them into a particular class. I have to predict the particular class. Okay, so in ImageNet challenge, we are dealing with the 1,000 classes, 1,000 or 10,000 classes. Okay, so that means a pretty quite big data set. Then after local classification, the second task come into localization. I have to locate the, so whatever I predicted, in this case cat, I have to locate that cat in that particular picture. So that is called as image localization. So this red box, if you can see, of surrounding the cat, is basically the image localization done by the CNN model, which is basic localization come as a regression task. Okay, because I have to find the pixel points of boundaries, so I have to calculate and find by through somehow some mechanism to found this coordinates. I have to print out this coordinates such that I can found a proper boundary box out of that. Okay, so this is the second task. Now third task is basically the object detection. That means instead of having one particular entity in the image, I can have multiple entities. Okay, so I can have multiple entities, like in this object detection I have cat, duck, dog. So these are related to my classes. So if any of these components which are present in my classes are present in this particular image, I need to detect that, and I have to give a boundary, a certain kind of boundary. This is called as object detection. Okay, so in this, multiple objects come into picture. Till now we will be looking at single objects. Okay, now once this part is also done, the next step is I need to particularly identify the segmentation. So now I said that okay, in this image I have cat, dog and duck. Now I have to exactly trace out the image where is exactly there's a dog, and where is exactly there's a duck, and where is exactly there's a cat. So this is an instance segmentation. Now you might, if you have used Instagram filters and all that, there the filters role is they're actually looking at your image and they're trying to trace out your face, and then on top of that they're putting certain image, certain kind of filters, right? So that actually the filters that you're using in your Instagram, Snapchat and all that, this come under instance segmentation, where your camera automatically detects the Instagram or any app automatically detect your face, the boundaries of the face, and then on top of that they will try to put certain other functionalities on top of it, so that you can use a filter, right? So these are very common image uh, problems related to CNN architecture, CNN and CNN are basically using for images, right? So this image class net is one of the popular challenges were there. It now right now it has been defeated now because we have more stronger uh, models right now, but during the time of 2010 to 2017, every company or many people wants to beat this image classification, such that they can given any image, I can predict within this 10,000 classes, I could predict which that image belongs to, which class it belongs to. Okay, so in this regard, multiple CNN architecture has been proposed. So for example, there's something called as AlexNet, that is, it consists of 8 layers of CNN. Okay, then since something called as ZFnet, it also belongs to 8 layers. Then VGGNet. So VGGNet is something we are going to look at in today's coding part as well. So I'm going to explain AlexNet and then followed by VGGNet. Okay, so it became quite popular after VGGNet. Many people, companies started technological companies started coming, and they're proposing their own net. There's something called as GoogleNet, which has 22 layers. So what are these layer consist of? I will talk in detail right now. And there's something called as ResNet. ResNet is from Microsoft. Now this has 152 layers. Now after this, after till ResNet, everything has been stopped. Like no more ImageNet challenge has been there, because it is giving us loss or the error of 3.59%, something like that. Okay, this is the error rate of like that, which is much better than even the human. So for example, given an image, human might misdetect it to at least 4 or 5 times out of the 100 times, right? So but the ResNet is able to perform well than the human, so that's why the ImageNet challenge ends here. So today we are going to mostly see the concept of AlexNet, VGGNet, and I will just give you a brief about ResNet. Okay, in code, the code collab notebook which has been shared, please share that again here, and it's running currently right now in the background. Here we will see mostly the VGGNet and the ResNet part. Okay, so this is the context of what we're going to see today. Mostly we try to cover most of the stuff during this part. Okay, so let's go to the AlexNet. So what do we mean by when we have saying that it has 8 layers? Okay, so in the um, uh, last session, which happened on Saturday instead of Tuesday, so we talk about something called as convolutional layers and something called as max pooling layers. So these are the very common layers that people started using it and try to combine them to form, and followed by, this is called as fully connected layers. Okay, now fully connected layers is nothing but what we have studied till now. Any neural network where each neuron is connected to all the neurons of the upper layers, that is a fully connected layer. But here convolution is something else. Convolution is a kind of a small convolution operation, a kind of filter. So it convolution might be a 3 cross 3 cross 3 uh, matrix kind of thing, where there's something called as width and height, and 3, this is something called as depth. Okay, now depth of any image belongs to a, let's say this input is there, so this input has 3 depth, 227 cross 227 as width and height. So this 3 depth is basically our RGB channel, that is red, green and blue. Okay, so if you're seeing a color image, the color image is belong to a combination of these red, green and blue channels. Okay, so since these red, green and blue, they have got one row as a third dimension, so that's what we are trying to say it as a depth. Okay, Okay, so this convolution operation usually happens, and that's why this name of convolutional neural network CNN come into picture, because of this convolutional layers where a filter, or you can say kernel, these are terminologies, of size 3 cross 3 cross 3 and or depth, I will say, rather than saying this 3 cross 3, 5 cross 5, 7 cross 7. So these are some filter size are there. So when we're saying filter, it's basically a number, a kind of matter, 3D matrices is there, which we are going to uh, run upon the particular input test. Let's say in this case image as a first layer, we're going to run on that. Based on that, we'll get a output. So that output will be a part of the uh, the convolution layer, which is the second layer. Okay, so just again to briefly recap what a convolution layer means. So let's say we have this 3 cross sorry, in 3 cross 2 this is the input, this is the image. Our image size is 22.7 dot 22.7 into 3. This is the input size. On top of it, I will apply a convolution filter of 11 cross 11 cross, and whatever the depth of the image will be. So in this case the depth is 3, so that's why we are adding 3. So if you can see, I am highlighting with maybe green right now here. So if you can see in the input image, so this is a 11 cross 3, 11 cross 11 kind of box you can see here. So that is a filter, and along with the same depth. So what it will do, it will go and each and every pixel of that particular image. So it will go by each and every pixel, and it will consider all its neighboring output. So let's say this is the image kind of thing, and okay, so I'm just showing for 3 cross 3 so that we can understand that. So this is the image green highlighted. Now I am putting a blue convolutional filter on top of that, where my focus will be the middle part, the top, the centermost element. So when I am putting a filter, I am putting the centermost element here, and I will consider all the neighboring information along with this, and I will calculate the average of it. So I will so let me say 1 2 3 4 5 6 7 8, and this middle point. So I will so whatever the values will be there in my filters, I will multiply that with the whatever the pixel values I have in the surrounding neighbors, and I will have a summation here, summation or average, summation or average. Okay, and based on that, whatever the values will be there, answer will be there, I will put that for this particular pixel. So that is a convolution. So an output of this convolution on applying a 3D image to a 3D filter, 3D filter and 3D image, sorry, 3D image, I will get output as a 2D feature map. Okay, because I am following the same depth and all that. So after following all this neighborhood information, I am getting only one pixel input from one convolution operation. So I will pass it on all of this data on of this all of these pixels. So one by one, if I do this for horizontally and then vertically, I will go, my convolutional filter will go horizontally first and then vertically. One by one it will calculate all the pixel size, and then it will give me a 2D output. Okay, now this is from one convolution, I will get feature map of one convolution filter. Okay, from one convolution filter, right? So but in general, I have in a typical convolution layer, I will have multiple filters, maybe 96 filters, maybe 100 filters. So the number of filters will be multiple, which we denote by k. Okay, and the size denoted by f is basically if I just write 3, that means f. If I write as 3, that means 3 cross 3 filter I am using right now, and the depth will be same as whatever the depth of the input will be. Okay, so now when you see in this image something called as 96 here, that means I have applied at the bottom where I'm just putting as red right now 96. So that means I have used 96 filters of 11 cross 11 size and applied on that. So after that I got a convolution layer which reduces the 227 filter with 55 by 55 width, and I will get this as an output. So how do we calculate that? So to calculate that, um, so I will just show for one example. So the first input was the same. Let's say, let's take this example itself. So our input is 227 or 227 cross 3. Okay, and a convolution layer, the first layer, has k, that is number of filters. Number of filters is 96 filters, because we know that these are 96 we are just decided, so we are taking 96 filter. And filter size is also given to us as 11 here in the image, right? So we will take filter size as 11 or 11 cross 11. Now there's something called as stride, which is keep and 4, and padding equal to 0. So what do you mean stride is? Stride means if in the above this, so here is so right now let's say I have a stride of 4 or 2. So I am calculating right now this pixel, the red highlighted one. So what I will do, if I do stride equal to 2, I will skip this part and this part, and which I am highlighting as a box right now. This part I will skip, and I will then again calculate for the blue highlighted box right now, which I am doing. Okay, so again I will skip these two this two pixel, and then again I will calculate another box, kind of like that. So the stride of 2 means I'm skipping certain pixels. I'm not going to calculate every pixel, because I have to reduce my number of computation. That's why I'm skipping few of the pixels on the time. This is the concept of stride. And padding means that so when I'm trying to, okay, here itself we can again see that. And padding means, so if I have to, when I'm using a filter, I have to fit this filter properly in the image. Okay, so but that means if I'm filtering this 3 cross 3 filter highlighted by blue onto this image, I am not able to I'm not able to process this 1 2 3 4 6 pixel. Okay, so let me highlight with black right now. So this pixel 1 2 3 4 5 6, or the highlighted one I'm doing, right, it will not able to do, because for that I have to have certain mechanism where I can fit my filter in such a way that I should have extra rows and columns. So to have the extra rows and columns, I will do padding with value 0 0 0. So if I do such kind of padding, then I can fit my filter, and I can play with I can calculate this 1 2 3, the highlighted black circle parts as well. So right now that padding is 0. Okay, so once I'm able to do that, then to calculate the output, sorry, to calculate the uh, output of what I am going to get, that is this convolution layer output. So what I can do is, there's a formula is there for W, I will say output as W2H2. Okay, and there's something called D2 depth, I will check that. So for W2 I will have to write Wi, that is in width of the image, my plus 2 into padding minus filter divided by stride plus 1. So this is my typical formula, by default formula. So where here Wi is the width of the input, P means padding, S means stride, F means filter. Okay, so if I add this to 227 plus 2 into P is 0 minus 11 divided by 4 plus 1. So if I do this part, I will get something called 55. Okay, so that means my output will be W2 and H2 will be always equal. So if I get 55 for W2, H2 will be always same. So W2 width and height will be always of same dimension, and depth will be equivalent to number of filters, because each filter will give me one 2D feature map of size 55 cross 55. So if I have 96 filters, so I will get 96 cross 55 into 55. Okay, so that's the output that we are getting here in this convolution layer as well, that is 96 cross 55, 96 of depth, 55 of width, and 55 of height. Okay, so this is a convolution, typical convolution layer. Now there's something called as max pooling. This is a second feature of convolution layer, that is called max pooling. So what max pooling do is to reduce, it will not do per se any significant computation, what it will do is, if I have a this convolution layer output like this, so it will take a combination of, max pooling layer like this, maybe 3 cross 3 pooling layer, and it, what it will do, it will find the maximum value out of this and then store it as a 1 pixel value. Okay, so it is only, so for example, for finding this pixel value on thing, so I will consider this 3 cross 3 pooling. So I will consider all these nine values, and I will find the maximum out of it, maximum value out of it, and then I will just store it here. So why max pooling we are doing? Just to shrink our order of computation, because still like this, in this output, earlier output was 55 cross 55 cross 96. It's a pretty big computation, so I have to reduce the computation route now because I have more layers where I can read. So what I will do, I will apply max pooling to reduce the size. So how they are reducing the size here? So if you can see in the max pooling, the yellow part, so this yellow part at depth will be as it is, has the earlier inputs, no changes here because we are not applying any filter here, only put 96 as this. And here we are got reducing our size of the image, or the intermediate image, as 20 cross 27 cross 27. Why? Because I have applied a 3 cross 3 max pooling. Okay, so if I apply 3 cross 3 max pooling, I will reduce, and with the stride of 2, stride means I'm skipping every two pixel, so two set of pixels. So because of that, so if I have 108 pixel, let's say, assuming like that, I will just only consider 57 or 59 pixel, not 55, 54 pixel, right? I will just consider only 54 pixel into my account, and then I will only calculate that. That's why I'm reducing the image width and height by half. So that's why 55 divided by 2 is roughly around 27. So that's why we got in 27. Okay, then after applying max pooling at this, again we want to take this as an input and apply a convolution filter. In this case, there's a filter of 5 cross 5. So you can check this 5 cross 5. I'll just use red pen now. So 5 cross 5 filter, and then my width will become 256, 23, 23. Now why I am telling all this calculation right now is because the major problem for learning any network, especially when it's so image, you should know that how a particular image getting transformed, right? If you're not getting idea that in which dimension it is you're dealing with, it's very hard for you to understand it in which point of layer you are right now and how much changes it is able to do. So that clarity should be there. That's why we are counting this, how many depth, that is how many filters are we having, how many width and height of my image would be after processing all this, after applying so much processing. Okay, another thing that you need to see, that after 96, I'm circling with red right now, after 96 my depth increased to 256. So what is exactly happening is that I'm applying 5 cross 5 filter, uh, and the number of filter on this a max pooling layer I'm applying is 256 filters. I'm applying 256 filter of size 5 cross 5. That's why my output consists of 256 values, because each filter will give me one output. So 256 filters will give me 256 output, and it will stack together. So that's why I'm getting computation of 256 thing. Similarly, after that I'm applying max pooling. So from 23, during max pooling we are not dealing with the number of filters, so the depth will be remain as it is. Only the width and height of the particular intermediate output will change. That is, apart from 23, it reduced to 11. It's not like every time it will go to have, it is the architecture. Okay, now after this there's a convolutional network here where our number of filters change, increase from 256 to 384, and the size of filter is 3 cross 3 itself. Okay, so that's how it will go. Then this another convolutional layer, then another convolutional layer of 256. Now till it here I'm lining with red, you're applying a proper convolutional CNN network. Okay, after that, after doing all this transformation, all this computation and all that, what you will do after that, you will apply something called as fully connected layer. Fully connected layer. So here what we have seen earlier, what we have seen in our earlier courses, earlier sessions, that if I have a simple architecture where I have 4 inputs and 2 hidden. This is an input layer, and this is a hidden layer, and this is the output layer, right? So in this, each neuron is connected to each other, right? Sorry, this. So this is like each neuron is connected to each other kind of thing, right? So actually that was what we are dealing with, fully connected, that each neuron is connected to the upper layer and the bottom layer properly, right? But because of this, the number of computations will be much higher. So for example, if I give, even for one layer, 227 cross 227 cross 3, that's a pretty high number. And if I do, instead of replacing, if I replace this convolution layer with fully connected layer, it will, the order of magnitude will be exponentially high. So we, to reduce that part, we are introducing this CNN network. Then after this, we are enforcing this uh, enforcing this fully connected network, which we are saying as, if you can see in the orange part. Now here 4096 4096,000. So what do you mean by that? 4096 is a 4096 number of neurons in this hidden layer. So the neurons here is 4096. Similarly in the second layer also 4096. And if you can see, I don't know whether you can see, this is something called as dense. I just circled it up. Dense means that all the neurons is connected to each other. So to take an example for this, so 496 cross 496, 4096, 4096 into 4096 number of parameters I need to calculate, right? After this, there's a 1000 layer. 1000 last layer is, this is a call as classification layer. Okay, this is classification layer because AlexNet challenge has thousand classes, so that's why we're dividing into 1000 layers kind of thing. Okay, so this is an overview of a typical AlexNet. So where we have an input with 227 cross 227 cross 3 as an image, and applying a number of convolutional layers and the fully connected layers to get a certain to get a proper image classification output. So now we have said that AlexNet has 8 layers, right? So 8 layers means this one, I'm just arrowing down right now, 1 2 3 4 5 6 7 8. So these are the 8 layers we're talking about. The max pooling layers we don't consider as one of the layers, because here you're not doing much of the computation as of now. Okay, so this is one thing. I want uh, I want to discuss about the typical CNN architecture. Okay, so you have to focus some of the convolution layers and the number of max pooling layers. Now there's, based on this, you should ask few questions, that okay, how should I decide that here the convolution layer should be, and then should be a max pooling layer as an alternate. Okay, that's the first question we should ask. The second question we can ask is, after having this convolution layer, I'm writing with red line, why these 3 layers are only convolution layer, why there's no max pooling layer? Okay, why no max pooling or any pooling activity we have included, right? So these are some of the questions we can ask right now, and the actual answer is we can't define it properly, the actual reason, because they have found it using empirical studies. So what do my empirical studies, like they have tried and tested multiple versions of placing the pooling layer and convolution layer side by side, and after that they arrived at this point of a particular network. Okay, apart from this, so the other questions are like, uh, how many parameters do we need to deal with? That's the first question. um, do we need to deal with? Okay, so this net is AlexNet has been proposed in 2000 net 2008 or 10. Okay, and the number of parameters it deals with in the order of 1 or 2 million. Okay, 2 million parameters, that means 2 million, maybe 2 or more than 2 million parameters you need to learn for this simple layer. Okay, now we are talking about large language models and all, which are having parameters in the range of billions, right? But even the simple model for classification, it is still taking 1 or 2 million parameters, right? So how many parameters do we need to deal with? That's the first question we can ask. Okay, then we can ask like, how many computation do we require? How many computation um, we need to require we required? Okay, based on that we have to see that, because depends on how much powerful your machine will be, right? That's why we need how many layers do we required, and what will be the filter sizes, right? How do we decide all this stuff, right? So especially our focus would be on um, the last two questions, that how many layers do we require and how what will the filter sizes, right? So let's say like here in the AlexNet I have one 11 cross 11 filter, then 3 cross 3 filter, 5 cross 5 filters, right? So how do I decide that this filter should be there, and how many layers? Why should I stop at 8? Why are not taken to 20, 30, or maybe why can't I stop at 4 layers, right? So these are the questions that honestly logically there's no particular formula that why we knew it do selected to this, but they have found empirically this. So the better answer is, rather than dividing from sky, it is typically told that to reuse the popular existing architecture and then tweak that architecture. Okay, so that's why the concept of pre-trained model is coming to picture, right? Because the people who have developed these models, they have tried multiple times, because it takes a lot of time, and this is one of simpler one. Now it's more and more complex race there, right? Or you might not have the resources to do that. So that's why what they say is it's better to use popular existing architecture and then tweak them little bit according to your needs, and then based on that you try to use this thing rather than dealing with scratch. Now you don't have to deal with why for a AlexNet I need this 8 layers or 7 layers or more than that. Okay, so I will stop 1 minute here and check if there are any question with respect to it. Then, because if you're able to get little bit just of the AlexNet, then we'll go to VGGNet, and based on that we will see that how it is working on the code. Okay, so all these names, numbers of layers fixed, but the parameter is supposed to be tuned um, individually or separately for the application, or these proprietary products sold by companies. Okay, there's nothing called as proprietary product when it comes to ML model as of now. Till that point that we are learning, obviously ChatGPT has this. The fine tuning part will come when you are adapt to the certain. If you know this whole network in and out, then fine tuning comes in the picture when. So let's say fine tuning when it comes. So let's say I have trained this model, right? So this AlexNet is there. I'm going to use that. Now it has been trained on 10,000 images. Okay, so let's say I have some 10,000 images and it contains truck, car, and all those stuff. Okay, now what I want, that now I get something called as electrical vehicle or supercars, electrical vehicles or supercars kind of thing. Okay, now I don't have these images in this 10,000 image class. Okay, this is the new images which are not present in the um, these are new images. Okay, I haven't trained this image. So what fine tuning will do is, I will use this AlexNet as a pre-trained model. That means its weights, everything has been learned. I don't need to train from scratch. What I will do is mostly is, yeah, someone raised the hand. Okay, just let me complete this explanation, then you may speak with respect to it. Okay, so what we'll do is, we, let's say it has 8 layers, right? So from 8 layers I will froze the 6 layers. Okay, and from the last 2 layers I will input, I give this input of supercars to as an input to these 2 layers. Okay, and based on it, try to learn that how try to learn these supercar images. Why I can do that? Because I have already seen car type of images. So while learning this supercar, I might able to detect how the car should look like. Okay, so it can able to differentiate between car, truck, and all that. It already do that, but not for supercars. So the model uh, task would be to learn the differentiate between car and supercars, maybe the way it is designed. Okay, maybe the color or something, right? It will do automatically. To do that fine tuning, we will only ask the model to train the last 2 layers, the rest of the earlier layers. So let's say in this AlexNet I will maybe uh, till here, let me say use black, till the black line I am keeping here, till this part I will not touch any of my train weights. Okay, this will be my pre-trained model only. And this, in this last two layers of here I will input as supercar images. So this is called as fine tuning. That means I'm going to tune the layer this existing architecture only for this, only for few layers to adapt to my inputs such that it will learn to a certain accordingly. Okay, so if I give this input as it is, this layers, the first six layers, or this all these layers will try to detect whatever they have done earlier, and after that the last two layers will try to see the difference between the existing data and the new data that they have. Okay, so this is the concept of fine tuning we are able to do. Okay, the proprietary, this thing is nothing that much, even we can do that, but the only thing is we don't have that much data and resources. So that's where the proprietary part come into picture. Okay, anyone has any other question with respect to this? No, you don't have to buy, this is already present. I will show you the through code that all this architectures has been proposed and it is open source. Anyone can use it, anyone can do it. Even see, even you can build ChatGPT as of now. Only thing is the number of data infrastructure to train such models, you don't have that. That's the only difference. So ChatGPT is based on a model called something called as GPT-3 GPT. Okay, now it has the version of GPT-3 and kind of like that. So they are engineers using it, but the core architecture is already available to any one of this. Anywhere, anyone can access that model. Only how they are training and fine tuning, that's not they're going to tell us on what data they are going to do it, and they might have found some tricks to do it very fastly. Right. So these are the things we are not going to tell us right now. Maybe at some point of time they may reveal that. Okay, but this architecture that you're seeing here, it's everything is open source. You can use it on your own also on your system for small data. Okay, so okay, let me quickly go to the VGGNet once, and then maybe I will tell you how to use VG, because I'm going to show the code part of VGGNet. So maybe you can understand that how you can use this VGGNet or AlexNet or ResNet uh, into your system. Okay, so that will give you much better insight of how to use these models. Okay, now the thing that we are going to deal with is this, I think 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So it has 16 layers VGGNet, that is we are going to build. It's already built, we are going to use it. Okay, so I just want reiterate what is this in this present is there, such that um, this part we are not going to see, we are not going to code. Okay, we are not going to code all of this part like earlier we used to code each and every layers and all that. Here we're just going to invoke a VGGNet function, or we are going to take a pre-trained model directly and going to run all this stuff. Okay, so I'm just showing you that how what are the values you're going to deal with. And this is one of the most prominent um, uh, CNN architecture, which actually make waves in the particular in the AI community, because after that only everyone started looking at the AI deep learning very seriously, because it gives very pretty good results with the for the ImageNet data set. Okay, so the input is basically is 224 cross 224 dot 3. 3 is for RGB, this is the depth. Okay, so whenever I'm going to say depth considered for the bottom pass where I'm writing here to 128 kind of like that. Okay, so this is the bottom cross depth. Okay, and width and height will be always same. Width and height for any convolution layer will be always same. Okay, so these are the few constant. Only depth most probably, all these three thing will change, but width and height value will be same, and depth will change based on the number of filters you're applying. When I'm saying number of filters means number of convolution filters. Okay, that's the one part. Second part is in this VGGNet, you're using only 3 cross 3 convolutional filters, nothing else. So in AlexNet you have seen that you have seen 11 cross 11, 5 cross 5 filters and all, but here we are keeping standard 3 cross 3 filter. The only difference where it's coming is how you are stacking up the convolution layer and max pooling layer. Okay, so for example, I'm just highlighting with red right now. It is the one I'm has circled red just right now. It is two convolutional network. Sorry, two convolutional layers, okay, of size 224 cross 224 cross 64. 64 is the number of filters that we have applied on the input, okay, and the width and height we have kept same because of something called as padding. Okay, so padding we have employed on this input, and because of that we get the exact same dimensions as the input image. Okay, so that's the first stack up of the convolution layer. Why they have stack up, there's no particular answer for that, but it's just like they have tried multiple combination and they found that this is turned out to be best one. Okay, now after this you applied a max pool layer where you divide the depth of 64 filters will keep as it is, only the dimensions of width and height will reduce by half. That is, right now it is kept as 112 and 112, so this will be like 112 cross 112 cross 64. So this is a max pool layer. Then after that we are increasing the filter. So after this output of this, we are applying a convolution layer, two convolution layers, one by one. So here our output will become, here as like 112 cross 112 cross 128. Okay, so here we increase the number of filters. So why we are what is the importance of this filter? Again, I want to tell you, reiterate this again. It's just like you're applying image transformation. Okay, so filters are help us, this convolutional filters are help us to understand the image transformation. So that means if I have an image like this, I might look, let's say width and height kind of thing. Okay, what filters can do is it might change the small it will try to understand the image through multiple transformation. Let's say, so it will might like it might transform the image as W and H, like it might transport it as a transpose. Okay, so let's say it is a colorful image, some image is there. So if it is a image is there, then a transformation will make it as a black and white image. Okay, so this one transformation can do, or it might able to detect the edges, so edge detection can might do. So multiple filters are, the role of multiple filters is basically to check one aspect of the image and try to understand the image through their lens and stack up all those value one by one. Okay, the reason we are doing this filters just to train the model, train the image, train the model to see the image from multiple transformation, and that's why there's so many convolution layers, filters will come into picture. Okay, then after that we are applying max pool of with 256 filters and reduce the size from, okay, so here after applying to the second max pool layer, we are converting the image size to 56, and from 56 we are converting to 28. So width, so if you can see that the size of the boxes is becoming smaller and smaller, so that's why we are having 28 cross 28 image right now. From 56 it has reduced to 28. So we are reducing one by one, and from 256 filters we are increased to 512 filters, and then we have 3 convolution layers, then followed by max pool layer, then again 3 convolution layers with max pool layers and all. So take your time, maybe you can take some time later to see these values. Again, maybe look at the lectures how we are calculating it, because you should know that how much transformation is happening and to what extent. Okay, from 224 plus 224 of a width of an image will come down to here max pool image, which is actually come down to 1 cross 1. Okay, which is pretty much significant, right? 1 cross 1. So from 224 we transform our images to such an extent that now it's a 1 cross 1 cross 1 into 512. 512 is the depth, the number of filters that we applied. right? After this, we are going to apply a fully connected layer of 4096 neurons, followed by last layer, which is basically a classification layer. Okay, so this is a typical VGG net. This is a typical VGG net that we are talking about, with uh, putting convolutional network max pool layer, arranging them in a certain ways to get a better understanding of the image classification. Okay, so if you can get basic understanding of net, why we are putting convolution layer, max pooling layer and all that, you don't need you just get an idea of this and just accept this. Maybe just try to accept this fact that they have tried multiple experiments, and based on that they found the best possible network according to their understanding, whoever proposed this network. Okay, now what I will do, I will show you the code for this, because I think it will be running, the running of the VGNet will already done, and such that we can see what how to code it actually, right? Actually there's nothing much of coding. uh, okay, let's stop staring. Okay, we just need to use the PyTorch library to, okay, I think the screen is coming now. Okay, yeah, good. So right now this model is, I think this part is running. VGGNet is over. I think it is running right now. Where it is right now? It is running the, this part is over also. This part, okay, ResNet, I think it is running right now. Okay, this part, okay, so still running. So because this model takes lot of time to train, that's why I didn't, instead of coding I just take it run, because it's running from last one and a half hour. So okay, that's fine. Let's start with what we have, this code is all about. I think, please, if whoever is not able to see the code, please, anyone from the chat box, please put down again the chat box so that they can access this code. So what we are doing is, we will take a CIFAR10 dataset. So what is CIFAR10? Okay, let me stop and share the dataset first. Just a minute. I'll share the entire screen. Okay, my screen is being shared. CIFAR10. Okay, so this one is one of the popular dataset in images, CIFAR10. There's something called MNIST as well. So we are now going to see a CIFAR10 dataset. That means this dataset consists of 60,000 images of width of height of 32 cross 32, and since it's a color image, we will assume that it has a 3 dimension, that is red, green and blue. So it is of 32 cross 32 cross 3 images with 10 classes. 10 classes are here: airplane, automobile, bird, cat and all. uh, and then the, with 6,000 images per classes. Okay, so 6,000 to 10, 60,000 images we have, out of which they had divided that dataset into 50,000 training and 10,000 test images. Okay, so this is a typical CIFAR dataset. This is one of the popular dataset that people use for learning and check their data as a benchmark. Okay, so this is what we are going to use today, and we will directly download using PyTorch. Okay, so let's see what we have. So we have some libraries called NumPy and Matplotlib for plotting, Torch for PyTorch, PyTorch Vision for basically for downloading the dataset and the model. Torch Vision has some function called transform. We are using that. Okay, and then for creating a neural network and finding the optimizer, we are using NNN Optim. Now we are running all this data on a GPU. Okay, so for that we are finding whether you have a GPU or not. In a Google Colab, you can go to notebook setting, edit notebook setting, and then you can select a GPU, that is T4 GPU, and then you can run it. I'm already using T4 GPU, so it is running in the background right now. Because the dataset is huge, the model is very huge, the number of layers are pretty high. So VGGNet that we're going to use has 16 layers and lot of millions of parameters to learn upon. So that's why it takes a lot of time. Okay, so we have from this code, the highlighted one, we have found that there's a GPU is present. So we are going to use that device GPU with device name to deal with our data. Okay, now what we'll do is we have used this train set. Let's before transform train, let's see at how to download a data set. um, so to download a dataset, we are downloading the CIFAR10. So we use torchvision.dataset.cifar10. So if we use this and command, we will put as in the attribute, we'll put root equal to data. So in this data folder, we are going to store download our CIFAR10 dataset. Train equal to 2, that means we are going to use this for training. That's why we are keeping the training dataset as well. If you put false, it will not download the training batches. Okay, we will going to download and we're going to transform. So what transform means, now the data that we are having is of 32 cross 32. Okay, so let me here. So the data we are going to get of image size is 32 cross 32 cross 3. Okay, but the input that we're going to take of any model might be differing, right? So we have to transform the data. That's the first part. The second part is the data will be in the form of pixel, right? So we have to convert that to tensors. So that is the second part that we need to do. After that, this another thing that we do apply on top of that, that is something called normalization, because the green, red, green, blue channel will be, it's a color image. The numbers will be varying. So normalization, what we do, we'll try to keep the values between 0 and 1. So that normalization doing, and this transform train that we are seeing here is coming from what we are defining here, the highlighted part in the above cell. Okay, so what we are doing is in the transform train, so this using transform as a function, we are calling of another function called compose. In that compose, first line, that is transform dot random resize cop. So we are converting a 32 cross 32 image into 224 cross 224, because our ResNet and VGGNet takes this input, okay, into 3. Okay, so what this resize cop will do is, based on the input of image, it will resize, it will extrapolate, or it will increase the image size from 32 to 224, or it will crop the image from 232 to maybe 16. If we say 16, it will crop it. Okay, so that is something automatically it will decide whether to resize the image or whether to crop the image. Okay, then we will convert into tensor, because PyTorch deals with tensors. Convert into tensors, the basic data structure that we have, and then we applying the normalization. So you transform dot normalize will apply normalization, where 0.5. So here we are dealing with, since we have 3 axes, XYZ, this is the 3 axes that we are having. So what we are doing is we are telling that our um, mean and standard deviation should be within the range of 0.5. So when we are applying the normalization, 0.5 will tell us that the standard deviation should be max to max 0.5 and mean should be 0.5. So that is the normalization part that we do in this, so that we divide, so we convert this whole 32 cross 32 into 3 into images into the normalization part. Okay, so this is for training. Same thing we have done for testing also. So why we are doing differently, let me show you why. So this is the file section, and here when we did torch vision dataset .cifar10, it is download the dataset here actually. Okay, and the CIFAR10 batches, if you can see data batch 1 2 3 4 5, this batches is basically for 50,000 images with each batch of 10,000 image. Okay, so that is what we are doing, and this is something on test batch where we have 10,000 image extra, and on this each batches they are trying to apply this transformation. Okay, so that is the purpose of that transformation that we are doing. Instead of having everything 60,000 directly on our system, it is not possible, so they divide into small batches. Okay, now after this we have defined a number of classes, because CIFAR 10 dataset 10 classes. Now instead of taking 10,000, we are going to show for batch size of 4 images. Okay, so to do that, this torch utils.data.loader, it will extract from train set the batch that we have seen the batches here, right? Data batch 1 and all, it will automatically take batch size of 4, we have defined 4, and it will take randomly, shuffle equal true means it will take any randomly 4 images and put that in train loader variable. Now from train loader variable we're going to iterate it using iter variable, and based on that we're going to extract images and label of, so what is the image and what its associate label is, so that is what we are extracting, right? So since we are taking 4 images, so the shape will be 4 into 3, 4 images, 3 into 224 cross 224. That's the transformation we have applied earlier. So this is the actual image of all the 4 images, okay? And size of one image is actually 3 cross 224 cross 224, and the final this 6 actually tells the label associate with the class associate with the image. So we have 10 classes, so from 0 to 10 and 0 to 9 any class will be associated to the image. Okay, so this is what we're done, and this is for showing the image. So I'm just skipping right now. So what this thing you can see later, but what it does is it will try to show the data. So I have taken 4 images here using for I in range of 4, so I've taken 4 images. So here you can see that this image is quite small and quite blurry, we can't identify it, but for each image we have something written 3838. That means whatever 3 class will be, I think it is a cat, class 8 is 3 and 8 class is boat. So it is this is the actual variable and actual images from the data set. So we're just printing it out. For that we have taken this, we have written this some code. That's not of our interest. More interest is about the VGG. Okay, so now VGG is, we are importing using models, torch vision import model, and we are right now we are not using train model right now. I will show you what we are doing. So we are just creating VGG16, which VGG16 means the 16 layers, and BN means batch normalization. That concept we haven't seen, maybe in the next session we will see the batch normalization part, but that model we have taken, and then we are printing the all the layers of the VGG. So it has 16 layers with in between some 16 layers with some in between ReLU as an activation function, so it is also adding the activation function and all. So how you can read this here is the first layer is convolution layer with kernel size of 3 cross 3, the channel depth is 3, the number of filters is 64, stride is 1 cross 1, padding is 1 cross 1. Okay, and after that they're applying some batch normalization. That is something we'll skip right now because we haven't seen that part. And on top of the whatever the output we'll get up from this, we'll apply the ReLU activation function on top of each value. Okay, then again we have a convolution layer. On top of we applying batch normalization, then we applying ReLU. After this, as in we will take this as an output. Whatever the output we'll get, we take as input and apply in the max pool 2D max pooling layer. So this is a max pooling layer that I'm highlighting right now. So just like that it is doing, and then later after this 43, if you can see after 43 our convolutional network will be over, and then we will take fully connected layer. So whatever the input that we are taking here, we will take this output here, we will take as output for this linear function where the number of, we are outputting number of features and the number of out feature is the number of neurons in the hidden layer. This hidden layer we are defining here. This will be another hidden layer, and this is a concept dropout. We will deal with deal with it along with batch normalization in the next lecture. And then we applied activation function, and then the final layer, it has only 3 layers. So the final layer consists of 1000 features, that is 1000 classes. Okay, so this is a VGG network, and if you want to see any particular layer, you can print out vgg.features. Similarly, any feature particularly you want to find it for classifier, you can find it out. So VGG features is for the convolutional layer, and the classification is the last part. Okay, now only change that we have to do in this, so when we're saying fine tuning and all based on our data, so the data that we have taken is CIFAR 10, that it has 10 classes. So now here we see the out feature is 1000, that means it has made for 1000 classes. Now we have to, if we want to reduce it to only 10 classes, so what we can do is, this code is there, there's another small simple one, but I will just explain you what you are doing. We are extracting the last feature, last layer, classification layer feature, and I'm creating another classifier called mod classifier. Okay, and in that mod classifier I am this num classes earlier we have defined as 10. So we are creating a new fully connected connected layer with 10 with 10 neurons, because we have 10 classes, right? So once we able to create this layer, we are going to add that into the actual VGG classifier. So this is the one way of doing it. That's here the fine tuning commit to picture. Okay, now if you go to the last, now here you can see that layer that we have changed from 1000, we have out features earlier was 1000, now we have kept to 10. Okay, based on our data set. Now based on this, you can look at the now again we are training this batch size. Now instead of taking 4, now we have to deal with all 50,000 60,000 data 60,000 data points. So we are going to train our VGGNet model on this batch size of 16. So it will take 16 images at a time and try to train it. This evaluation code is basically for telling that what is the input, correctly input and wrong output. So it is basically for finding the accuracy of the model. Okay, so this VGT2 device means we are using for, since we are writing for this as a GPU code, that's why device is coming into picture. We are going to transfer the model directly on the device. Okay, and then we are going to find the loss function using cross entropy, and then we have defined the optimizer of stochastic gradient descent. So this is the actual code where it's going to run, where the epoch we are keeping as 1, because the whole training data set, it's taking a lot of time. It takes lot, maybe 20-30 minutes to train one model. So that is what we are going to do. For one epoch we are going to turn with the data with batch of 16 size. One by one we will take the input to the GPU device. We'll calculate the gradient. Based on the gradient, we'll output the images, whatever the output. We'll then calculate the loss function. After loss function we'll do the back propagation. So let me just write it down. Calculates the gradient. This calculates the um, predict the output, calculate loss function, and then it do back propagation. Okay, and then based on that update the weights. And since it's quite, the data is quite huge, so what we are trying to do, we are trying to delete the input labels and outputs that we have found here, the input, this inputs and all, such that our memory will be saved. Okay, that's we are doing. And after every 100 iteration we are printing the loss function. So we are like this, for every iteration we are saying what is, at which iteration we are having, and which, at what loss we are and right now what is the loss of our current model. So this is what we are trying to do, and later we are going to append the what are the loss items. So for after every 100 iteration we are printing the loss function. So like this. And that see, since we are only training for one time, the test accuracy is very bad. It is very less than even random classifier, that is 16.65, and training 16.44, because the model hasn't trained the number of, we have to deal with hyperparameters, so we haven't done the hyperparameter tuning much. So that means we have to see changing the learning rate and the number of epochs. But based on this code you can try to tweak it out later, because it will, each epoch will take at least 20-30 minutes. So that's why we are, and just for demonstration we are showing it here, but obviously you can change the test accuracy. Okay, I think it's already 7:10. Maybe we take a break of 5 minutes here, come by 7:15, and maybe then after that I will let you know that how to use a pre-trained model. Right now whatever we have used here is training the VGG model from scratch. We have just taken the layers and just training the model from scratch. Now what we'll do, we will use a pre-trained model of VGG already, which is pre-trained, and then we're going to see the how the result would be like. Okay, so I will stop sharing. If you have any question, please let me know in the chat. Otherwise we will take a break till 7:15. So okay, then we'll come back by 7:50 in that case.
इसको इसको रिमोट एक्सेस है ना?
नहीं है एक्चुअली, द प्रॉब्लम इज इट्स नॉट कनेक्टेड मैन और अपना वाईफाई पता है,
ओके
तो इसलिए रिमोट एक्सेस ऐसे भी एक्सेस नहीं कर सकती, बट प्रॉब्लम वही होगा कि
वाईफाई
वाईफाई अगर फ्लक्चुएट होता रहता तो एक्सेस नहीं कर सकता। हमने डिमांड किया है, बहुत दिन से अभी तक आया नहीं है, कॉन्फ़िगर नहीं किया मैंने। Yeah, hello, welcome back. Um, so maybe I have maybe another 30 seconds before starting. So I just want to know one thing with respect to have you people started coding or something with respect to the developing a simple CNN or the basic uh, fully connected network? Have you tried that? Because unless you people tried that, there's a hard choice that you may not be able to go through them part. So I just want to know whether from either yes or no that have you tried this code part as of now. Okay. Okay, that's fine. Maybe you should start because there's a possibility that it might go overhead of you right now. But okay, let's continue this. Maybe you can refer the recording later as well. That's not a problem. Um, so let me share the screen again and okay, so where we were, so what we have seen as of now is uh, we wrote some code where we have taken the model of VGG directly, we put that in GPU, and then we put the input data, output data on the GPU and try to calculate, perform the all these gradients, loss function, back propagation on that on the VGGNet. Right now what you can see here is the outputs are little fluctuating. So for example, at one iteration, at 200 iteration the loss is 2.71 and the 300 iteration loss for 2.30, right? So it is quite fluctuating, and also we are not getting the best model. So maybe around this, by the time it is coming there, the output what we're getting from this test accuracy, train accuracy we are getting is that the last iteration that we have got, right? So this not might be the best possible method. So what we can do is something like checkpointing, and before checkpointing, let's see that uh, how to you run the same code with a pre-trained model. Now I'm not going to run um, train that whole from startingly. What I will do, I will first take the pre-trained model with the learn weight itself. Only maybe I will freeze the earlier layers and just keep the last layer intact. So how we do that? So for this, we are again setting in same batch size equal to 16, and when we are loading it, the from the train set, we are taking shuffle equal to true, and test size we are putting shuffle equal to false because we don't need to actually shuffle the test input, right? We are just because testing on that. Okay, now if you want to use a pre-trained model directly, that there is a VGG16. So what we are keeping pre-trained model equal to true. Okay, so when we take pre-trained model, it will download the pre-trained model. Like you can see the pre-trained model is approx 528 MB. Okay, then what else you want to do is, now if you're going to learn uh, if you want to fine tune this VGG model, you don't want to change the whole model weights, right? So what you will do, you will put this param required grad equal to false. That means all the layers that you are keeping right now, what you're going to do, you're only going to keep it as false data. Okay, so keep as false, that means you're not going to change the model, so it will freeze the earlier layers, freeze the earlier convolutional um, convolution, pooling, and some fully connected layers. Okay, freezing means no updates in weights. So this is the concept of freezing. Come into picture. So then what I will do is, earlier we have seen the code of 4 lines of code here, where we know that our output, um, let's go up, yeah. So earlier the output feature, the VGG model is trained for 10,000 classes, say 1000 classes, but our data set contains only 10 classes. So we need to uh, modify our last classifier layer as only with output of 10 features, right? So we written this highlighted part of code. Much easier part of code that we can do is um, writing this feature, writing this part. So we will say, we will take the last layer in feature, we'll put it in one variable, finally in feature, and in that we just put the layer called nn.linear, and just put this VGG classifier. We'll just up, and on top of that we will just rewrite the final layer as final in features, whatever the features are, and the number of classes equal to 10. This num classes we already defined. So here we are again change the um, final layer, which is a classifier layer uh, with 10 neurons instead of 1000. Okay, now once we do that, um, what we have to do is for this final parameter, uh, here we are going to tell that okay, for this final layer, this VGG classifier, the last layer with 10 neurons, we are going to update the weights within this layer. Okay, before that everything will be freeze, but only for this layer we are going to do that. So for that we will say VGG parameters in param, and that is the last parameter. For this we will show that it has 10 cross 496, that is from last layer to second last layer to last layer, and the final parameter will be it will output as 10. That means only it has contained only 10 value. Okay, so that is the param shape will be. So this is the only last layer only is going to be weights going to be updated, rest of the model will be remain as it is. So once we are able to do that, then we are going to, now this VGG model is complete. We know that only the last layer has to be learned, that is last layer has to be fine tuned. So for fine tuning part, we will after keeping according to our needs, which needs layers need to be learned, which layers not to be learned, then we are going to pass this VGG to the GPU device, um, initialize the cross entropy loss and the stochastic gradient descent as an optimizer. Okay, then we are going to run only one epoch because it takes a lot of time, and for iteration the number of iteration times 50,000, that is the training size, divided by batch size here is 16, so it comes to 325. So 325 number of time it will iterate, taking batch of 16 images one at a time. Okay, it will take the input labels from the data, that is from the train loader. It will calculate that, it will take the data batch size one by one, and it will put that to the device, that is GPU, and then it will calculate again, it will calculate the gradients, it will predict the outputs, it will find the loss function, and then it will do the back propagation. After that it will update the weights. So these steps is typically common, just one line of code we can do this, and after every 100 iteration we are just finding the loss item. Okay, and then to remain, because we have dealing with very high data, that's why we have to, in between whatever the irrelevant data that we are having, for each iteration we are deleting it. That's why we deleting the input labels, because input labels are coming from the batch size. So once this earlier batches are over, we just delete that batch and take in the new batch, right? And similarly the output, that is a predicted output, so we are just removing this predicted output also, because we are input has been changed. And then whatever the cache we have for the earlier iteration of the images, we just remove that, so that we can have a proper memory space to learn more data. Okay, so once we do that, this is the output will look like. Here this code is basically for uh, printing our per every 100 iteration. So here you can see that a loss will start with 2.34, and in between it went till 1.18 at 500 iteration, and again it is increasing. It is quite a fluctuating. So that's one of the problem with deep neural network, that uh, after every, even though it's very deep, the 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 chance of say thinking that it might overfit is not so obvious here, because during propagation, because the number of layers are pretty much high, there's a problem of gradient vanishing will come into picture, and that's why the weights may not update as seamlessly as we think of. Okay, so after pre-trained model, if we're using a pre-trained model, it is this part of the code run much faster than the existing one where we train the VGG model from scratch. Here we taken the pre-trained model directly and only change the last layer. So it given us a much better accuracy than earlier. Earlier was 16%, now it is like 42%, right? So that is one thing with respect to this. But as we have seen, this 42 accuracy that we have found here is it's coming at the last point, like that's at the 3125 iteration we found this test accuracy. But we have earlier seen that our smallest accuracy loss that we have found is at 1.18, right? So we need some ways to we need to find certain ways to uh, what to say to store the best model that we are finding during training. Okay, because the last epoch doesn't mean that it might give us better training model, right? In between also we might find a better model. So that's why the concept of checkpointing will come into picture, right? So how we'll do that? So here the only difference will be in the code will be this part. So where at each iteration we are checking that whether the min loss, so min loss earlier kept to 1000, and after that after each epoch, each iteration, we are finding the loss function, and if it is less than mean loss, earlier min loss variable, so we are just keeping that as a min loss, and then we are copying that particular weights of that particular state of the model using deep copy. So once we are able to do that, we are keeping the store in the best model. Okay, and then once our whole iteration, the whole epoch is done, then take that best model we will take that best model here, we will load the state using best model, and then we evaluate and do our accuracy test. Okay, so this is what the meaning of checkpointing. Much better way of checkpointing is also there, but this is the much more manual way of doing this. Other ways are also there, which we'll see over the course of another 2 or 3 sessions. Okay, so checkpointing is one of the ways where you find that your model is at better state right now, so use that state to and save that state weights and all everything into picture, and then when it comes to evaluation, that is evaluating your test data, at that time use that as best model. So based on that, our accuracy is not much increased, but increased to 45%. Obviously we can do some more changes in the hyperparameters and number of epochs and all, because we have done only one epoch, right? So we can do hyperparameter changes to increase this iteration. So what you can do is maybe it will take this code and change some hyperparameters to improve this VGG model, because its actual accuracy when we have tested with multiple parameters, it reached to 80%, 90% also, right? So more chances of possibility is there. It's just that right now for demonstration purpose we have shown only for one epoch, because one epoch will take 20-30 minutes. If you take 10, 15 epochs also, it might take a whole day, right? That's what. Okay, so we have seen the VGGNet as of now. Now it's time to look at uh, the ResNet model. So this is uh, the best model for the ImageNet challenge. So let me just put it here, ResNet model, PyTorch. Okay, so this ResNet model is there, and it has uh, what you say, uh, different variation, that is like ResNet 18, 34, 50, 101, 152. That means this number shows a number of layers with respect to it. Okay, so these numbers will tell the number of layers, and we are going to take a ResNet 18 as the example. So I will just show you how the ResNet look like, but this ResNet is actually this ResNet 152 and ResNet 101. They are the one who actually beat the ImageNet challenge, and it shows much better in performance with respect to humans. Okay, so if you click on any of this, um, you will uh, learn about their documentation. You can learn about them, that what is the parameters are there, what else you can do about it. Okay, so this is there. Apart from that, there's a proper paper is also available. Here I think we can find it here itself, right? uh, so the is based on this paper. Let me open this. It's taking some time. Okay, so deep residual learning for deep residual learning for image recognition. Okay, something is happening. Okay, fine. uh, yeah, so maybe you can read this paper also. It explain for particular model in a much deeper way. Okay, if you read these few 2 or 3 papers, you will understand that how this CNN models are come into existence, and what is the particular rationale about choosing certain aspect. Okay, now I will show you the ResNet model discuss the ResNet model for a few minutes, and then again we'll come back to the uh, this model. Here we're going to actually use a pre-trained model, and we will see that so ResNet will look like, see, it's quite big with respect to it, so we will see how to read upon this part. Okay, so let me stop sharing and share the screen. Okay, so yeah, I think the screen is coming now. Okay, so I think it's quite clumsy and it's very short image. I should have make it big, but okay, I will tell you what is written here. So this is the typical VGGNet, okay, of 19 layers. Okay, and this top one, it's a ResNet, not ResNet, a simple network with 34 layers. Okay, based on that we will build intuition how it comes down to this part where you can see certain arrows are there, right? So we will see what does it means like that. Okay, so we will see what is there. If you're not able to read, that's totally fine. I will just let you know, go through this part once. Okay, so the question of ResNet started with a simple question that how deep a number of layers can go. Okay, so that means, yeah, right. Okay, so question started when Microsoft people ask that what happens when you increase the depth of the network. Okay, depth of the network means if I increase my convolution net layers. Okay, that's what they asked. Okay, so what they thought that if we increase the convolution layers, what we'll find that it might give us better performance on training data. Why? Because the model became very complex, so that means this might lead to overfitting of the image, overfitting of the data, training data, right? So that's what they thought of actually. But what actually happened, that when they compare, so what they do in the same paper that I showed earlier, so what they do, they compare this not 34 but 56 layer uh, CNN layer, okay, and 20 layer VGG. Okay, so what they found that VGG, this VGG perform better for both train and test data. Okay, so that was quite strange because if I have 56 layer, that means I have more complex layer, okay, more parameters to learn upon, so that means I should have done overfitting part, right? So that was the intuition, but what they found out, even the less number of layers are performing much better than the in both training and testing. Forget about testing also, but training also it is giving us this. So what they hypothesize, um, sorry, so what they hypothesize that uh, so what they thought that maybe the gradients are not learning better, are not learning in a better way. Okay, that means somewhere in the network while learning the parameters, somewhere the gradients have been lost, or they got stuck. That's why the updation is not happening properly, and that's why the learning is not happening properly. Okay, so uh, uh, so that was happening. So what they thought, okay, let's do another thing. So they thought that, okay, if that is the happening, so what I should do is, so let's say I have this four layers, right? So these four layers I have, so what I should do is, um, this all are convolution layers. So in between, so we have a very big layer, big deeper network, and we have this 4 convolution layers. Let's take a part of that network. Okay, so what they thought, the output that I'm getting here, the output I'm getting here, can I attain the same output maybe in this part? Can I get that part? That means, let's suppose it has a matrix of 3 cross 3 and I get an identity matrix. That means only the middle part is 1. Let me try to show it better way. So let's say the output of this convolutional matrix is something like this. So I'm getting this as output. Now can I again get this output same here after applying 2 convolution layer or not? Okay, that's a kind of thing they have thought of. The reason is they thought, so if I somehow able to after okay, so why they thought is because of VGGNet. So what is happening in VGGNet, that it has only 20 layers. Okay, so in 20 layers they have kept everything in same as, they have kept everything similar to uh, sorry, they kept everything similar to the VGNet, except they added few more layers. They have added 15-16 layers extra. Okay, so what they thought, that wherever we are adding extra layers, can we get the same kind of output um, from the earlier one? So let's see here. So if you can see here, I'm circling right now. So if you can see, there is some space here in this is a VGGNet. Okay, and then here some space is there. Okay, so and here also. So these are some extra, the circle red highlighted one, these are some extra layers. So what they thought, somehow by some computation, can I bring the output of the layer before the circle to the final layer of output? Because this is what if we are able to do that, at least we are able to reach to output of similar to the VGG net. Okay, because it's performing bad, so first we need to reach to the equivalent performance of VGG net, and after that we will see how to improve, right? So that was the intuition. So what they thought, can I bring my input from the output from this particular, let's say I'm highlighting with green now, uh, with the circle green layer to the output green layer. Okay, the same way how the VGGNet has done, right? So I need to do certain computational complex layer with respect to it, but they found that it is quite hard. So what they did, they applied simple technique, something called as residual. So what residual is doing, that after every two layers, it is taking the output from the last two layers and adding to the new input. Okay, that means if you can see here, I'm highlighting with green now in the image. So whatever the output that I'm getting at this max pooling layer, I just with green dot, I'm adding with the output of whatever these two layers I've got after transformation of the input. I'm adding with it. This, let's say, so for example, at particular instance I have a output as x. Okay, and after two layers I'm getting certain output. So let's say f of x, after applying two transformation I'm getting something called as f of x. Now what the ResNet the authors are saying, that after getting f of x I should add again the x part. Okay, so I will add this residual again here. Okay, so what will happen, that because the problem gradients are not falling properly in the layers, so what I will add, so I will keep on adding the past information data to the newer learning transformation. So once I am able to do that, maybe I can actually learn the past information properly and I can update some weights in a much better way. Okay, so that is what the people try to put it into way. That's why ResNet is also called as residual net. That means I will um, keep considering my past or the earlier convolution layer data for further processing. Okay, so that is the concept of this residual net will come into picture. I will show you the diagram in the paper in the from the another device. I will show you that, but that is the concept here, right? So because of this simple concept, that is I'm taking the earlier input output data as a input to the newer layer. Because of that, my model is able to train much better. Because of that, my gradients are learning better. Is if gradients are learning better, my back propagation will happen properly, my updates in the weights will happen properly, and based on that my model will learn the image in a much better way. Okay, so this is the concept residual in the ResNet is there. Now ResNet consists of one multiple layers, that is 152 101 layers and all that. So it's similarly consists of max pooling and conversion layer, nothing more than that. Okay, so because of that it became very successful. Okay, so I will stop sharing as a this part theoretical part, and I will show you that what the residual part come mean by. Just give me a minute. So just let me share the screen. Okay, and just open this paper once. Okay, so earlier I said, right, so what they have done, this paper has shown that they have taken a 56 layer model and a 20 layer model, which basically is VGGNet. Okay, even in training error and the test error, it is showing that training error is 20 for 20 layer and test error for 20 layer is much lesser compared to 56 layer, right? So to solve that problem, they produce the residual learning. Okay, so what they're doing, so this here some convolution layer will be there. Here the weight layer is basically one convolution layer. Okay, so output of the earlier convolution layer, that is taken as x, it will taken as an input, and will add it to the output of the second weight layer I'm highlighting with here. So it is, that is fx plus x, and then after that they will apply some ReLU activation function. Okay, so that is what it's trying to do. It will take the earlier convolution layer data and it will add to the newer data. Okay, because of this transformation, they have found that they have found that the machine is able to learn much in a much more better way. Okay, so if you can get this concept little bit clear, uh, then what or maybe you can read the paper also later. Let's go back to the code here. Okay, now so what we're going to do is a pretty big network. I will show you here. So we have taken the pre-trained model directly instead of taken this architecture here. So we have taken the pre-trained module. We can write as pre-trained equal to true. Okay, now to see the ResNet, here we have done this part. So here we have a simple convolution layer. Okay, and applying the batch normalization and ReLU activation function, and then we have done a max pooling. Okay, now there's something called as basic blocks are coming into picture, right? There are basic block 1 and basic block 2 kind of thing. So basic block 1 basic block 2 means that I have a block where I'm stacking the convolution layer with different sizes. Okay, so here I have a convolution layer 2 stack up to each other. Okay, so that is one thing, and then I have another block of convolution layer with 64 filters of kernel size 3 padding 1 and all stack up together. Okay, now once I'm able to do this, whatever the output I've got from this convolution layer 1, I will take it as an input here. Okay, then I will add whatever output I'm getting from this after this computation, and this taken this input, I will take them as a um, I will take them as a input, and I will pass it to this block. So this block will be, I will just highlight this part, right? So here this block considers a residual learning. So here I am taking the earlier blocks data as a output data as an input and try to learn from it. So similarly more layers are there, total 18 layers are there, and follow it after which we have a last adapt. So after this they are doing adaptive pool layer, and for after there's only one fully connected layer with 1000 features, which we have to convert to 10, which we have done earlier also. We have converted to 10 features because we have a 10 classes only, right? So to freeze the first, to um, freeze the layers, in freeze the layers, we are doing this param requires grad equal to false. So that means we don't need to update any gradient, any weight parameters. So that's the first thing. After this, we are updating the last layer, updating the last fully connected layer with 10 neurons. That because we have 10 classes. Okay, so once we do that, and then we are stating that only for this particular layer we are going to learn the gradients. Okay, so here we are saying that we are going to learn the weights for the last classification layer. Okay, so for that, that is the size of 10 into 5, 5 and 2, like 5 and 2 is the input and final output is 10, that is final output is 10 like this. Okay, so once we are able to done, that is our ResNet, that we have modified the ResNet, pre-trained ResNet, and then we have given this to device is GPU here, um, putting the loss function as cross entropy loss. Parameters, you're using a optimizer of stochastic gradient descent with learning rate of 0.01. You can change it also. And then we have trained this model for 4 times, for 4 epochs, with keeping track of loss as well. Here we so what we are doing, we are trying to find the best model using the concept of checkpointing. So with min loss, wherever we found the minimum loss during the any iteration, we are keeping that as a best model. How do we do that? We're using copy.deep copy. So we're going to copy the whole ResNet model parameters and going to put that as a best model. Okay. Similarly, earlier, we are going to take data into the batch size. So data, this has a batch size of 16 images. Okay, 16 images. We'll take this as an input. We'll put that in GPU device. Calculate the uh, gradient descent, gradients. Calculate gradients. Calculate gradients of weights. You can say like that, and then predict the output. Predict output. Predict loss. Predict the calculate loss, and do back propagation, and then update the weights. Okay, this is for finding the best model. The sorry, finding the best model during the training. Okay, checkpointing, and then we are printing out the loss after every 100 iteration, and we are deleting the in between variables, input labels and outputs. That is because it is there with respect to batch size. With each batch size we are calculating them and deleting them. Okay, and then we are appending the loss, and we are evaluating the final model, how it will show like. Okay, so if you can see here, it started with something, yeah, it started with min loss of 2.47, and after each whenever there's an iteration, there we are printing the min loss whatever we're finding, right? And after every 100 iteration we're showing the actual loss. So like that, when you are seeing the min loss, that means after that particular 100 iteration, they are finding at particular iteration we are not printing which at which iteration we are finding the less and less loss. So we went till maybe 0.47, 0.45 loss, and 0.53, 0.4745. So we are doing for each epoch. So we have done for 4 epochs. So we have went till a loss of 0.41. Okay, and this is how it will look like, 0 till 0.41. But our test accuracy is still 55, 56%. For 56% we can say like that. Okay, so after more hyper tuning parameters, we might get much better results, because, and also it's a 18 layer. If we take 150 layers or 101 layer, where it actually perform best, if we take that, it might get the accuracy of 97-98%, but it will take a lot of time to train as well, because the number of the bigger the data, bigger the network, the deeper the network, the more time it will take to train, and also it depends on the data set as well. Okay, and then we have taken the best model, uh, sorry, this output that we are getting here, 55.96 and 56.48, this train accuracy that we are getting here is based on the last iteration, but from the best iteration also we are getting similar result, that is 56.434, 56.42 kind of thing. So that means that there's not much difference from the best model as well, it is giving almost similar kind of output. Okay, so this is what we have seen. So today we have seen the maybe a little bit background of convolution layer. So I just repeated uh, the what we have seen in the last lecture, that is a convolutional the understanding the convolutional architect layers basically, and then we have seen the VGGNet, we have seen the ResNet, and then we have seen checkpointing in the freezing layers of a particular convolution layers. Okay, so that's what we have seen as of now. I'm so that is from my side as of now. Let me see, I think there's some comments are there. Okay, share the architecture and theory doc link also. Okay, theory, okay, I'll sh I'll just share this, just a minute. So here in this folder I will updating based on the date virtual class, I will update the theory doc as well. Okay, but the training accuracy will be highest at the very end, or the exactly stage when the run the one loss. Okay, the training accuracy will be highest when the loss is less, but it is not every time, it might not be true. Even we get the very less loss, the chance that the accuracy is not that high. Like for example, we got the loss of 0.41, uh, but we got the loss of 0.41, but still the accuracy is 56 point something. So so even though it's positively correlated to each other, directly correlated, but not every time the drastic change will we can see, because there's a high chance that the model is still not able to learn all the images properly. Okay, but the what the accuracy that we have seen in the before. Okay, let's show you the what I'm talking about. So the accuracy that we are seeing here, I'm highlighting right now, the test accuracy and train accuracy, it is at the last iteration. So at last iteration, whatever my model weights are, based on that, I'm getting this final test accuracy and train accuracy. Okay, nothing more than that. But from the best model, when we're doing checkpointing, it is also found that it is giving a better result, but not that much better result. Even though our loss is like here, our for ResNet, our min loss is 0.41, and the training accuracy at the last iteration shown us near to 56%, right? But even with the best model, we are still at the 56% only. The only performance gain is like 0.1 or 2, right? 0.1 or 2 increase in performance, that is not that much. So that is something you need to look at while training and testing part. Okay, that's why checkpointing is very much important, because while you're doing multiple epochs and you might leave the model to train in your machine for maybe 2-3 days or month, obviously you may come in between and you find that okay, one at particular instance my model performed very way better, but by the end of the training you found out that my model is not as better, that what you see intermediate. That's where the checkpointing part will come into picture. Okay, any other question with respect to this what we have seen today? Because that's the end from my side. So if you have any other question, please let me know. We still have some time. You can unmute yourself as well. Okay, so I'm assuming there's no questions. So that's the end. the lecture from my side. So next lecture we are going to see the batch normalization and dropout. These are a few important concepts before we need to learn. We will also see the how to visualize CNN, and then we will look at, if time permit, we will see the sequence learning problem, because that will lead to RNN. Okay, so that's the end from my side. Thank you very much. I'm stopping the recording, and class is end from my side.